Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. In this video lesson for intermediate thermodynamics, we'll be looking at stability. Our goal here is that we'll be able to define the criteria for stability in pure substances. In the last lesson, we ended by looking at this table briefly. We had talked about the fact that at equilibrium, entropy will rise to a maximum, and that gives rise to thermal equilibrium, that temperatures will be constant, mechanical equilibrium, pressures will be constant, and chemical equilibrium, the chemical potentials will be constant throughout a system at equilibrium. And then we briefly said that you could use fundamental relations to also extend this to some of our energy functions. The two that are most significant to us are Helmholtz energy A and Gibbs energy G. And as entropy goes to a maximum, A and G will go to minimum values, meaning that their differentials should go to zero at equilibrium. Today we want to look at stability. So if we have a maximum and ds is 0, how can we differentiate that from being a maximum or a minimum? And this is going to be our stability. So let's go first to some little diagrams to kind of get at the concept of stable equilibrium. Stable equilibrium is one that if there's a small perturbation, it's going to return to the original equilibrium state. Now, if you look at the first diagram here, you'll see that I could shove that little marble quite a ways and it would return naturally to that lowest position. On the other hand, the unstable, the center diagram, if I let that little marble move at all, it's just tumbling on down. That's an unstable equilibrium state. I may get it to hold for a second, but it's not going to stay there. But we also have metastable equilibrium states. And in a metastable equilibrium state, the size of the perturbation matters. A very small perturbation might just rock it up that hill a little bit, but it would come back down to this stable position. But if I have a very large perturbation, it'll move it right on over that little crest, and it will rest in a stable final position at the lower equilibrium states. So size of perturbation is going to make a difference between something that's truly stable and something that's only metastable. For real systems, we're typically going to reach what will be a metastable state. And we're going to describe these in terms of some sort of rate expression or a kinetic expression. And so we're going to describe something as being at equilibrium when we don't notice a change in the state. So the rate of change is too slow to be significant within the time span that we're interested in. I typically get bored looking at a system that is nearly at equilibrium within just moments. But if I'm doing experiments, I might wait longer, minutes, even hours, before I declare that I'm at equilibrium. When I have multiple variables, this can get a little bit more complex because I need to be stable in all directions. The concepts of mechanical and chemical equilibrium describe this, where I have to have not just the temperature being constant throughout the system, but I also need, for the case of mechanical equilibrium, the pressures to be constant throughout the system. Or for chemical equilibrium, I need both temperature and chemical potential. Again, we will never really be reaching a stable state. I'll be reaching metastable states where over the time period of interest, I'll see no changes. Now, the second law of thermodynamics really is our definition of stability and equilibrium. The second law says that I'm going to reach a maximum in entropy when I'm at equilibrium. And we can look at this for an isolated system, or we can do it for a system in combination with its surroundings. It really doesn't matter. The second law applies in both cases. At a maximum, ds will be 0, but I also have a concavity to guarantee that it's a maximum and not a minimum. And normally, from our calculus background, we know that this says that I need the second differential or second derivative to be negative in all directions. Now, if this happens to be 0, then I'm going to need to go to the third derivative, the fourth derivative. I'm going to keep taking the next level of derivative in all directions until I find one that is negative, truly negative, not 0. Okay, and this is going to be a mathematical requirement for being stably at equilibrium. Now, the key here is that this change in S needs to happen in all directions. So if we look at what this means for something where S is a function of, n plus 2 variables, okay, number of components plus 2 additional, then I end up with expressions here where differential of S, I just take the derivative with respect to each of the individual variables and multiply by the change in those variables, and that's the differential of S. But for the second differential, I need to take all the possible combinations of second derivatives. Some of these will be like the second derivative of S with respect to volume twice. But some will be things like the second derivative of S with respect to volume once and internal energy once. So we're going to have those mixed partial derivatives. And as I need to move up to higher and higher orders, I get more and more complex expressions. So how does this get us to energy maximum principles? There are many ways you can do this, and you can simply work through fundamental relations. But we have always kind of had a sense that U and S are tied together. There are sets of postulates. Callan and Modell both have different sets of postulates that are used to kind of be our anchor for the core things we know about thermodynamics. And one of these postulates that they use is that the entropy of any system is going to vanish, or be 0, in the state where the change of U with respect to S, while I hold volume and internal, or number of moles, constant, will be 0. Again, if you go from the fundamental relation, du is TdS plus PdV minus PdV plus mu dn's for all of those possible components, what you're going to see is that, yes, indeed, this has to be true. Now, what this leads to is that as long as S is reaching a maximum, I'm also going to have du that's going to reach an extremum. However, when I look at the signs on my U second derivative and my S second derivative, I see that U is going to need to be positive, whereas S is going to be negative. This leads to the fact that this extremum in U must be a minimum. Again, we can do this with other energy functions, but this is just the basis of the idea of how one can develop these rules. In our next lesson, we're going to be looking at some results that we get from this stability criterion for equilibrium. Thank you very much for your time.